Hello guys, welcome back to Maison African Motives. Still working on electrotechnics N4, that is working on revisions on principles of electricity. We are going to focus on the question paper which was written in June 2022, where we are given the first part was to define the following terms. In this case, we've got the first part, which is the electromotive force in this case. So if you have to check, we described this in the previous class, but let us have this as the electric pressure which causes, so here we are given this as the electric pressure which causes the current to flow between the 2 points in a circuit. So that is what we call the EMF, or what we refer to as the EMF in this case. All right, then the second part is the resistivity. Also, you're supposed to know the units, guys. All right, so the resistivity can be given as the measure of the resisting power of a specific material to the flow of electric current. Remember that resistivity given as rho in this case, which is the electrical resistance of a conductor of unit cross-section area per unit length. So that is the electrical resistance of a conductor of unit cross-sectional area and unit length. So that is which is the same as the measure of the resisting power of a specific material to the flow of an electric current. So that is our resistivity in this case. All right, then let us check the other part, which is the Weber in this case, the unit Weber. Remember, this is from our magnetic there. When we are dealing with magnetic circuits, we are dealing with magnetic circuits. We've got flux density. All right. So Weber is the amount of magnetic flux which, when cut at a uniform rate by a conductor in 1 second, generates an EMF of 1 volt. So that is what we refer to as the Weber in this case. So that is the amount of magnetic flux. Talking about the magnetic flux density, we're talking about the amount of magnetic flux there. All right, then the other part, which is 1.14, that is permeability in this case. What is it that we know about permeability? The space that we have in between. So this is the ease with which a magnetic field can be established in a material compared to the ease with which the same magnetic field can be established in air. That is the permeability. Then we have got the last part, which was reluctance in this case. So each part is actually 2 marks times 5. So each part is 2 marks, 2 marks, and so forth. All right. So reluctance is like resistance. The same way, if the same way that you understand the resistance, that is the same way reluctance operates as. So it is the opposition offered to the establishment of magnetic lines or force in a magnetic circuit. So remember, reluctance is in a magnetic circuit, where resistance is on an electric circuit, the opposition to the electron flow, which is the current flow. So as long as you understand resistance, therefore take that into a magnetic circuit. Now you are opposing the establishment of the magnetic lines in this case. That is the opposition of what? The magnetic lines in a magnetic circuit. So that is how you can actually memorize the formula. I mean the definition for reluctance in this case. All right, let us check the other part of our question, which is on 1.2. All right, 1.2, if we check here, we're given information: a copper conductor and aluminum conductor are connected in parallel and carry a combined current of 250 amps and so forth. Then after this information, the question is, take note, guys, what you're given here. Without calculation, make D the subject of the formula. In our syllabus, the change of subject is actually a core part that you need to understand, the basic part that you need to know. So here, the calculation is not, which means the information here that we are given is not even necessary. That is what we do not need this. The question is without calculation. So this information was just a disguise that you are given. What we need is to operate from the formula that you are given to make D the subject, which is the diameter. So as you can see here, this formula was actually wrong. We are given that R is equal to rho over area, of which we know that R is equal to the resistivity times the length over the area in this case. So, but here we were given our formula as resistance is equal to resistivity over area. So according to what you were given, this is what you were given a hint. So we are going to use the one that you're given, but the actual one is this one. So I'm going to also show you on this part on the actual formula. But according to the one that we are given, which is this one that I'm saying it's wrong, we are supposed to have rho L over the area. So remember that area is equal to pi d squared over 4. So what you can simply do in this case, let us first start by cross multiplying so that we can properly see our area in this case. So if you cross multiply, you are going to have a R which is equal to the resistivity divided by the resistance, divided by the resistance. In this case, we can obtain our area being equal to the resistivity over the resistance, whereby our area is given by pi d squared over 4. Remember, what we need is to make d the subject of the formula. So we can substitute in place of area. We are going to substitute pi d squared over 4, which is equal to the resistivity over the resistance. So since we want to focus on the diameter in this case, what we need is to remove the pi over 4 in this case. So in order for us to remove this, we can simply multiply it by the inverse of pi over 4, which is 4 over pi. But what we do on the left-hand side is to be done also on the right-hand side. So the moment you multiply, these will cancel together. You remain with a d squared. So that means d squared will be equal to, in this case, if you multiply 4 times this resistivity, we are going to have 4 resistivity over pi times radius, which is pi times radius. So to make d the subject, definitely introduce the square root to remove the square that we are given here. So our diameter is going to be equivalent to the square root of 4 times the resistivity over pi r. In this case, everything is under the square root according to the formula that you're given, because this is an error from the department, so we are going to use it as it is. But like I said, the exact formula that we know for the resistivity is this one. So from this formula, meaning to say your answer was going to be equal to the first part, you're going to cross multiply just like the previous part. You're going to have RA is equal to rho L over that is resistivity times the length. You can even substitute your area here. Let us just change the calculation a little bit. So this is going to be R times, remember our area is given as pi d squared over 4. So this will be pi d squared over 4 in this case, which is equal to rho L. So what you can simply do is to cross multiply. This is like over 1. So 4 is going to multiply this side. 1 is going to multiply this side. So it's 1 times R pi. So this is going to be pi R d squared, which is equal to 4 times this part, which is going to be 4 times resistivity times the length. You divide by pi r. Since you are multiplying in this case, this can divide so that you remain with d squared. So that means our d squared is going to be 4 times the resistivity length over pi r in this case. So to find d, what you can simply do is to introduce the square root, just like the previous part. To remove the square, we introduce the square root. So our d is going to be the square root of 4 times the resistivity times the length over pi r in this case. So as you can see, the difference that you're supposed to have is here having L. On the actual formula, we are having L. Here we are not having the length, of which, as long as you talk about the resistance, it has to be affected by the length. It has to be affected by the diameter, which is giving us the area. Once we do not have the length, therefore, we can't have the resistance of a conductor. I don't know what to be calculating, because here we are also given the length. If you take note, the length of each conductor the length is supposed to be there. So this is just an error which happened. All right. So like I said, from these two that you're given, this is the first one from the error that we had. And the one that maybe you worked with the corrected formula, this one, your answer is going to be having your L on the final part. All right, so that was it. Let us check 1.3. We are given that a generator in this case of 100 volts and a battery of 75 volts with internal resistances of 0.4 ohms and 0.3 ohms respectively are connected in parallel to a supply. All right, so we've got two things here, a generator and a battery. These two, they are connected in parallel. All right, so let us just try to have a sketch. Use Norton's theorem to draw. Norton's theorem does not draw a diagram, guys. All right, so this is just an error also on the asking of the question. They are just supposed to say, draw a fully labeled circuit diagram. That's it. Then you use Norton's theorem to calculate this part. All right, so that is another thing that our students might have a confusion to say, well, how do I draw a Norton's theorem? How do I use Norton's theorem to draw a diagram? Okay, anyways, that is to answer this question is you're supposed to apply the Norton's theorem. All right, so like I said, let us have our diagram. We have got two things here, a generator and a battery in parallel. They have internal resistances, remember. All right, so this is it, guys. So this is 1.3. So we are going to have a generator. Remember, a generator, we can just have a symbol here just to indicate a generator, but it's not important. What we need is the voltage here. So we are going to have our generator. It has its own internal resistance connected in parallel to a battery. So here we are going to have a battery. So we are going to have our battery in this case here. This battery also has its own internal resistance. So let's just put this away. So we've got internal resistance like this. So there we are told that this is later connected in parallel. Okay, so let us see what we are given here. So this is connected in parallel to a supply of load 35 ohms. So the supply is having a load of 35 ohms, which is the resistance. So this is connected. So we've got a load resistor here of 35 ohms. So this is what we are given. It's connected in parallel to a load resistor of 35 ohms. So this is our load resistor. 35 ohms in this case. All right, so let us take the information onto our diagram, the battery and the generator. The generator, it has got 100 volts, internal resistance 0.4. Remember, this is respectively. So the first one is for the generator, 100 volts versus 0.4. So this is 100 volts, our generated EMF in this case. So we can just have it as E1, which is 100 volts, having internal resistance of 0.4. We say this is 0.4 ohms. Then for the battery, we are having a voltage there at the battery, the EMF of 75 volts corresponding with the internal resistance of 0.3. So that's 75 volts versus 0.3. So you're going to have this as E2, which is 75 volts versus R2 of 0.3 ohms. All right, so this is the diagram that we have. So this is 1.31. So this is 1.31. Actually, the first part was just to draw a diagram. Like I said, that's it. Okay, everything is there. So that's 4 marks for that, just to have this diagram. Then on 1.32 is to calculate the voltage drop across the 35 ohm resistor. Remember, the 35 ohm resistor is the load resistor in this case. This one, the 35 ohm resistor. So we need the voltage drop across the load here. So we need to calculate a VL, which is the voltage drop. So how can we calculate VL in this case? That means we need to calculate the load current using the Norton's theorem. So remember, I talked about the Norton's theorem on a separate class. So make sure that you watch the video so that you can understand to use the Norton's theorem. So that can help us a lot. All right. So remember, from our Norton's theorem, I was saying the first thing that you're going to need, because here, the moment that you need, you calculate this load current, that means you multiply the load current and the load resistance, you can have your VL. From this part, we are saying the load voltage is going to be current times resistance. So that is the load current times the load resistance. So you can see that the missing part that we have is the load current here, which is the one that can be calculated from our Norton's theorem. All right. So like I said, the first thing that you're going to need is to have introduce a branch AB across the load resistor. So you're going to short this load resistor. So our circuit is just going to be like this. So like I said, this is just a battery, guys. This is just, I mean, just a source of voltage where we've got a plus and a minus. So you can just have it as a normal voltage source, the one that we are used to. Then we have got our resistance here, internal resistance to V2. In this case, this is our E2 with its internal resistance. So the first thing, like I said, is to introduce the branch AB by short circuiting the load resistor. So we short circuit the branch that has got the load resistor in this case, which is the 35 ohm. So the moment we do this, we are going to calculate the short circuit current. So at that moment, we calculate the short circuit current, which is our Norton's current in this case. All right, so this is where we are going to have our short circuit current, which is IN across the branch AB. All right, so that's it, just like this, guys. As you can see here, we've got our E2, which is 75 volts, our R2, which is 0.3 ohms, our E1, which is 100 volts, our R1, which is 0.4 ohms. So we can calculate this short circuit current if we are to apply our Norton's, our Kirchhoff's laws. They state that this is our positive, so current is flowing this way. So our current from this branch, we're going to have current 1. This is our positive, so current is also flowing this way. So we are going to have our current 2. These currents, they enter the branch here from the node that you're given. So we are saying the currents flowing towards this junction, which is at this junction here, which is I1 and I2, will be equal to the current flowing away from the junction, which is IN, which is our short circuit current. So that means our IN is going to be equal to I1 plus I2. These two flowing towards the junction, this one is flowing away from the junction. So that means we can calculate these currents. Let us just have these ones aside. I1 can be calculated from E1 versus R1 since we've got voltage and resistance. So I explained this on a separate video, like I said. So that's 100 divided by 0.4. So that means I1 is going to give us 250 amps. So this one was going to give us 250 amps. Then I2 is going to be E2 over R2. So we've got E2 and R2 here, which is 75 volts over 0.3. So we are going to divide 75 divided by 0.3, which is 250 amps. So we have obtained our I2. So like I said, our short circuit current, which is the Norton's current IN, is going to be taken as I1 plus I2. I1 being 250 amps plus I2 here being 250 amps also. So if we add these currents, we are going to obtain 500 amps. All right, so we have obtained our short circuit current, which is our Norton's current. Then what is the next stage? We go back to our original diagram here. This is our original diagram. All right, so this time, this is what you're going to do. You remove the sources. Okay, you are going to take out these sources that you are having. Okay, you remove these sources, the voltage sources, replace with their internal resistances. So and calculate Rn in this case. So we are going to have these voltages removed, replaced with internal resistances like this. So we are going to have R1 and R2 in this case like this. All right, so we've removed the voltage source on the generator. We also removed the voltage source of E2 of the battery in this case. So this is what you're going to have. And you calculate what is referred to as the look-in resistance, which is your Rn, your Norton's current in this case, Rn, that is the look-in, the way that you check from this point, these two resistors, they are in parallel. So that means we have got R1, which is 0.4 ohms, and R2, which is 0.3 ohms. So the look-in resistance tells us these are in parallel. So that means we can apply the product over sum concept to calculate Rn. All right, so that's it, guys. Let us calculate our Rn in this case using product over sum. So we are going to apply product over sum. That is R1 times R2 over R1 plus R2. So let us substitute our values. R1 being 0.4 times R2 being 0.3 over 0.4 plus 0.3. That is the sum of the resistors. So this is going to give us Rn in this case. So Rn being our short circuit current is going to be 0.7, 0.1714 and so on, which is 0.171 to 3 decimal places in ohms. All right. So we have our short circuit current, our Norton's resistance, which is our short circuit resistance in this case. So now let us have these on the equivalent circuit. After finding Rn and calculating your In in this case, remember we calculated In here, we got 500 amps. We are going to take this into the equivalent circuit, all right? So we are going to have our Norton's equivalent circuit. So that is our equivalent circuit in this case. So the Norton's equivalent circuit, I explained it also before, that it consists of the Norton's current, which is our short circuit current. So we are going to have our Norton's current here, the resistance that we calculated, our Norton's resistance, and connected to the load resistor. Remember before we removed the load resistor, so we're going to bring that load resistor back. Remember our purpose is to calculate the load current. So here we are going to have our load resistor, and our load resistor was the one that we removed before, which was 35 ohms. This is the 35 ohm resistor. So that is our load resistor, so that we can calculate our load current from there. All right, so our load resistor, we say that was 35 ohms, and this is our Rn, which is from our Norton's calculations. Rn here was, all right, I think it's on top here, 0.171. That's 0.171, all right? So we're going to have 0.171 ohms. And here we've got our short circuit current, IN. That was 500, if I'm not mistaken here, IN, this one, which is 500 amps. All right, so that's it from this part. We've got 500 amps. So how are you going to calculate the load current from the equivalent circuit? So your formula is going to be given as IL from the current divider rule. We are going to have Rn over the sum of these resistors. So it is going to be Rn over Rn plus RL times the current, which is our short circuit current, which is our Norton's current here of 500 amps. So that means the load current, we're going to substitute here 0.171, everything over the sum of the resistors, 0.171 plus 35 ohms in this case. All right. Then we multiply to the total current, which is our short circuit current, which is a 500 in this case, the one that is going to branch into these two branches here and here. So that is, we are going to obtain our load current in this case. All right, so that means if we are to use our calculators properly, our load current is going to be 2,43098 and so on, which is going to be 2,431 amps to 3 decimal places. So the question was not to calculate the load current. The question is to calculate the voltage across the 35 ohm resistor, which is the load, the voltage across the supply. So the voltage across the supply is taken from this part. We have got IL in this case. Remember IL, we have got 2,431. So we can calculate this voltage from current and resistance, like I said before. So that is going to be product of the load current times the load resistance. So that means our VL, the load current of 2,431 amps times the load resistance of 35 ohms, that is going to give us VL. So that will be, in this case, we are going to obtain something like 85,085. So that's 85,085 volts. So this is how we can apply our Norton's theorem in this case to calculate the voltage. What you need is the current from the Norton's theorem. We wanted the current, we can calculate the current, but after calculating that load current, we can take it as an advantage now to calculate the voltage. Since we've got the load resistance, we've got the load current, we can calculate our our voltage in this case. All right, so that was our question in this case, which is here, which was having 9 marks. All this part was having 9 marks, as you can see here. All right, let us check 1.4. We have got on our magnetism concept. All right, so let us check on our magnetism here. All right, so that's too much. We are given, in this case, a straight conductor, 50 centimeters. All right, so let me just try to push this side so that I can increase a little bit so that we properly see. Okay, I think this will be enough. All right, so let us take our information first. We are given here a straight conductor, so that is 1.4. Our straight conductor has got a length of 50 centimeters. So remember, your length is supposed to be in meters. So divide by 100, that will be 0.5 meters. Is moved at right angles. At right angles, meaning to say our angle is 90 degrees. And at right angles, remember that this does not affect anything, since sine 90 degrees is equal to 1. So it means that there is no effect at all. But at right angles, our theta is 90 degrees. To a magnetic field of, so it is moved at 90 degrees to a magnetic field of flux density. So we are given the flux density in this case, which is B. So our flux density is given as 0.3 Webers per square meter. Remember that the Weber per square meter simply means Tesla. In this case, that is the Tesla. And we've got the velocity of 8 meters per second affecting. So our question is to calculate 1.41, the magnitude of the EMF induced in the conductor. How do you calculate the EMF induced in the conductor? From the information that we are given here, also we are given this formula from our formula sheet. So we know that the EMF is equivalent to BLV. So that is a BLV sine of theta for a certain angle. Maybe it's not 90 degrees, because 90 degrees, like I said, sine 90 is equal to 1. So this one does not affect us. So we're going to just have our E as a BLV. But provided that there's an angle, maybe 60 degrees or it's 30 degrees, you have to include the sine angle that you are given. All right. So that is how we can answer this question. So as you can see from our formula, all we need is to substitute back. We've got everything. Our B being 0.3 times the length in meters, which is 0.5. So that's 0.5 times the velocity in meters per second. So our velocity, it's 8. So that's E is going to be, if we multiply properly, we are going to obtain 1.2 volts in this case. All right, so that is how we could have calculated the voltage, which is the EMF. Then 1.42, the force required to produce this movement from this information that we have, if it ends of at the ends, or suppose this movement at the ends, if of this conductor is supposed to be at the ends of this conductor, are connected to the circuit drawing 600 milliamps, which is the current in this case. So we are given the current, and we need to calculate the force that is going to be required. All right, so that is 1.42. So we are given a current in this case of 600 milliamps. How do we calculate the force from the current? Remember that force is equal to, so the force now is the product of B Li in this case. That is, if you are given an angle which is not 90 degrees, you're supposed to use sine theta for that concept. But here, because of 90 degrees, like I said, sine 90 degrees is equal to 1. So our formula is going to remain as BLI. So what we need is to simply substitute our information. We have got the magnetic flux density of 0.3. So our force is going to be magnetic flux density of 0.3 times the length in meters of 0.3 times our current. Remember our current, that's 600 times 10 to the exponent of -3 for milli. This part of milli amps. Milli is to the exponent of -3. If it is micro, that is to the exponent of -6 for microamps. All right, so this is going to give us the force, knowing that our force is measured in newtons. So we are going to have 0.0 0.09 newtons in this case. All right, so you can convert to millinewtons if you want, or you can just leave your answer like this. You are done. All right, so these are the typical questions, as you can see, the ones that you might be given on our magnetism part. That is what we had. So this was 30 marks on everything on principles of electricity. Just imagine if you understand this topic and you've got 30 marks, all these 30 marks, it means you just need 10 marks from one topic to have 40 marks. You have already passed the exam. So guys, let us revise as much as we can on the principles of electricity, DC machines, working with AC. Just at least 3 topics that you can master as much as you can, you know that you're already above half. All right, so this is how you can attempt these typical questions. All you need is to work on more question papers, see how do they ask these questions, so that when you revise, you know which areas to focus on much according to your syllabus. Okay, guys, that's what we had from Mason African Motives. Till we meet again.